It works on my machine. The most dreaded phrase in all of software engineering. You've spent days building a feature. It runs perfectly on your laptop. You push it to production, and everything breaks. Different operating system. Different library versions. Missing dependencies. Your teammate pulls the code, and it doesn't even start. Docker fixes this forever. And in this video, I'm going to take you from complete beginner to confidently using Docker in production. Let's go. Before Docker existed, deploying software was genuinely painful. Here's the scenario. You're a developer working on a Python web application. On your Mac, you have Python 3.11, a specific version of PostgreSQL, certain system libraries, and everything works perfectly together. But your teammate is on Windows. They have Python 3.9. Their PostgreSQL is a different version. Their environment variables are different. You push to production, and the server runs Ubuntu with completely different configurations. Suddenly your app crashes with cryptic errors about missing shared libraries or incompatible module versions. Sound familiar? This is called environment inconsistency, and it plagued software development for decades. The first solution the industry came up with was virtual machines. A virtual machine emulates an entire computer. It has its own operating system, its own kernel, its own everything. You could package your app inside a VM and say, "This VM works, ship it." But VMs are heavy. They take gigabytes of disk space. They need minutes to boot. Each VM runs a full operating system copy, which wastes enormous amounts of RAM and CPU. If you needed to run 5 services, you'd need 5 VMs, each consuming gigabytes of resources. We needed something lighter. Something that could package an application with all its dependencies, but without the overhead of an entire operating system. Enter Docker. Docker uses a technology called containers. A container is a lightweight, isolated environment that packages your application and everything it needs to run. But unlike a virtual machine, containers share the host operating system's kernel. This is the key insight that makes containers revolutionary. Let me explain the difference clearly. A virtual machine includes a full guest operating system. It needs its own kernel, its own system libraries, its own everything. A container shares the host's kernel. It only packages the application layer, your code, your libraries, your dependencies. Nothing more. The result is dramatic. Virtual machines use gigabytes of space. Containers use megabytes. VMs take minutes to start. Containers start in seconds, sometimes milliseconds. A single server that might run 3 or 4 VMs can easily run dozens or even hundreds of containers. Here's an analogy that makes this click. Before shipping containers were standardized in the 1950s, loading a cargo ship was chaos. Every item was a different size, a different shape. Workers had to figure out how to stack everything manually. It was slow, expensive, and error-prone. Then someone invented the standard shipping container, a uniform box that fits on any ship, any truck, any crane. It didn't matter what was inside: electronics, furniture, food. The container was the same size, handled the same way. Docker did the same thing for software. It doesn't matter what's inside the container: a Python app, a Java service, a Node.js server, a PostgreSQL database. The container is the same standardized unit. It runs the same way everywhere. Any developer, any server, any cloud provider. Now let's talk about 2 important concepts: images and containers. These terms get confused constantly, so let me be precise. A Docker image is a blueprint. It's a read-only template that contains your application code, runtime, libraries, and configuration. Think of it like a class definition in programming or a recipe in cooking. A Docker container is a running instance of an image. When you start an image, it becomes a container. One image can spawn multiple containers, just like one class can create multiple objects. The image never changes. Containers are live, running processes. So how do you actually create a Docker image? You write a Dockerfile. A Dockerfile is a simple text file with instructions that tell Docker how to build your image, step by step. Let me walk you through the key instructions. First, from. This specifies your base image. You almost never start from absolute scratch. Instead, you build on top of existing images. From Python 3.11 gives you a base with Python already installed. From Node 20 gives you Node.js. These base images are maintained by the community and available on Docker Hub. Next, workdir. This sets the working directory inside the container. It's like using cd in a terminal. All subsequent commands run from this directory. Then, copy. This copies files from your local machine into the image. Copy copies everything from your current directory into the container. You can also copy specific files, like copy requirements.txt. Run executes commands during the build process. Run pip install minus our requirements.txt installs your Python dependencies. Run npm install installs your node packages. These commands run once during the build, and their results become part of the image. Finally, cmd. This defines the default command that runs when a container starts. Cmd python app.py means whenever someone starts this image, Python runs your app. Here's a complete example. Imagine a simple Python Flask application. Your Dockerfile would look like this. From Python 3.11 slim. Worker/app. Copy requirements.txt period. Run pip install minus our requirements.txt. Copy period. Cmd python app.py. 6 lines. That's all you need to containerize an application. Now you build the image with docker build-t myapp period. The -t flag gives it a name, a tag. Docker executes each instruction in order and produces an image. Here's something beautiful about Docker builds, layers and caching. Each instruction in your Docker file creates a layer. Docker caches these layers. If you change your application code but not your requirements.txt, Docker reuses the cached layer for pip install. Only the copy of your changed code gets re-executed. This makes rebuilds incredibly fast. To run your image as a container, Docker run myapp. Your application starts in seconds, completely isolated, with all its dependencies included. No conflicts with anything else on your system. But where do images come from and where do they go? Docker Hub is the default public registry. It hosts millions of pre-built images. Need PostgreSQL? Docker pull Postgres. Need Redis? Docker pull Redis. Need Nginx? Docker pull Nginx. These official images are battle-tested, regularly updated, and ready to use. You can also push your own images to Docker Hub or to private registries like Amazon ECR, Google Container Registry, or GitHub Container Registry. This is how teams share images and how CI/CD pipelines deploy them to production. Now let's talk about networking. By default, a container is isolated from the outside world. If your app inside the container listens on port 5000, nobody outside can reach it. You need to explicitly map ports. The command is docker run -p8080:5000 myapp. This maps port 8080 on your host machine to port 5000 inside the container. Now you access your app at localhost :8080. The format is always host port :container port. You can map any available host port to any container port. Multiple containers can even use the same internal port as long as they map to different host ports. Containers communicate with each other through Docker networks. By default, Docker creates a bridge network. Containers on the same network can find each other by name. If you have a container called Postgres and another called WebApp on the same network, WebApp can connect to the database using the hostname Postgres. No IP addresses, no complicated configuration. Next, volumes. Containers are ephemeral by default. When a container stops, any data written inside it disappears. This is by design. Containers should be stateless and reproducible. But what about databases? What about uploaded files? What about logs? Volumes solve this. A volume is a piece of persistent storage that exists outside the container's file system. You mount a volume into a container with -v. For example, docker run -v mydata:/var/lib/PostgreSQL Postgres. Now the PostgreSQL data lives in the volume mydata. Even if you destroy and recreate the container, the data persists. Now here's where Docker becomes truly powerful for complex applications. Docker Compose. Real applications aren't single containers. They're systems with multiple services. A typical web app might need a web server, a database, a cache, maybe a message queue. Docker Compose lets you define all these services in a single YAML file called docker-compose.yml. You specify each service, its image, its ports, its volumes, its environment variables, and how services connect to each other. Then one command, Docker Compose up. Everything starts together. Your web server connects to your database, connects to your cache. All isolated, all reproducible, all defined in code. Your teammate clones the repo, runs Docker Compose up, and has the entire application running in seconds. No installing PostgreSQL. No configuring Redis. No fighting with environment variables. It just works. Let me walk through the most common real-world use cases for Docker. First, development environments. Every developer on your team gets the exact same environment. New hire on day one. Clone the repo, Docker Compose up, start coding. No 3-day setup process. No outdated wiki page that's missing half the steps. Second, CI/CD pipelines. Your continuous integration server builds and tests code inside containers. Every test run uses a fresh, identical environment. No more flaky tests caused by state leftover from previous runs. The container that passes CI is the exact same container that deploys to production. Third, microservices. Each microservice runs in its own container with its own dependencies. The authentication service can use Python. The payment service can use Java. The notification service can use Node.js. They don't interfere with each other because they're completely isolated. Fourth, local databases. Need PostgreSQL for development? Docker run Postgres. Need MongoDB? Docker run Mongo. Need Redis? Docker run Redis. Each one starts in seconds, uses minimal resources, and can be destroyed and recreated instantly. No installing database servers on your laptop. No cluttering your system. Fifth, legacy applications. Have an old app that only runs on a specific version of Java or a specific Linux distribution. Containerize it. The container packages that exact environment forever. You can run it on any modern server without modifying the host. Now let's talk about Docker in production. Docker solves the packaging and deployment problem beautifully. But when you run dozens or hundreds of containers in production, new challenges emerge. What happens when a container crashes? How do you scale from 1 container to 10? How do you distribute traffic across multiple containers? How do you roll out updates without downtime? Docker alone doesn't solve these problems. You need container orchestration. The most popular orchestration platform is Kubernetes, often abbreviated as Kubernetes. Kubernetes manages your containers at scale. It handles scheduling, deciding which server runs which container. It handles scaling, automatically adding more containers when traffic increases. It handles self-healing, restarting containers that crash. It handles load balancing, distributing traffic evenly. It handles rolling updates, deploying new versions without downtime. Docker Swarm is Docker's built-in orchestration tool. It's simpler than Kubernetes, but less powerful. For most production workloads at scale, the industry has standardized on Kubernetes. The relationship is simple. Docker packages your application into containers. Kubernetes runs and manages those containers at scale. Docker is the format. Kubernetes is the orchestrator. Let's recap the entire Docker pipeline. You write a Dockerfile that defines your application's environment. You build it into an image with Docker build. You run the image as a container with Docker run. You share images through registries like Docker Hub. You map ports to expose your app. You use volumes for persistent data. You use Docker Compose for multi-service applications. And in production, you use Kubernetes to orchestrate containers at scale. The core mental model is just 3 things. Dockerfile produces an image. An image runs as a container. That's it. Everything else is details built on top of these 3 concepts. Docker eliminates the phrase, "It works on my machine forever," because with Docker, your machine, your teammate's machine, the CI server, and the production server all run the exact same container. In the next video, I'll cover Kubernetes, how to orchestrate thousands of containers at scale, handle automatic scaling, self-healing, and zero downtime deployments. If you're building anything with Docker, you'll eventually need Kubernetes. Subscribe so you don't miss it. I'll see you there.